I expect you to be able to reproduce in an exam, but it's a nice proof because it revises our notion of order of an element. It's about a little bit of number theory with the lowest common multiple, and it's a very useful result. So what I want you to be able to do is, well, I want you to be able to understand the proof, and I want you to be able to use the result. So what we've just proved is that the lowest common multiple of the order of x and the order of y gives you the order of xy. Well, again, an induction argument shows that you can apply this not just for the product of two group elements, but a product of an arbitrary finite product of group elements, as long as they all commute and pairwise their cyclic subgroups intersecting just the trivial subgroup. So although I won't prove that, we're going to apply this to products of more than two elements, okay? But that does require an induction. So what we're going to do now is apply it to permutations. And there are some questions about this kind of thing on the worksheet, and you'll also meet similar things on the coursework. So let n be a natural number, and let's take a permutation in Sn. Then we know that sigma can be written as a product of disjoint cycles. Let's think of a suitable letter that I haven't used recently. I've used quite a lot of letters recently, haven't I? I don't want to, let's think. I'll use little u. I don't think I've used little u today. So this is writing sigma as the product of disjoint cycles. So we know we can do that by our theorem from last week, and we saw it in examples, and I'll do an explicit example in a second. Now, another thing we did last week is said if we've got two disjoint cycles, then they commute. I think I proved that towards the end of last week's lecture. Any two disjoint cycles commute with each other, so that's one of the hypotheses of the theorem. And so let me just observe that for all I and j, tau I, tau j is the same as tau j, tau I. So any two of these commute, and if I look at the corresponding cyclic subgroups, then if they're disjoint cycles, the only thing in here can be the identity, which I'm tending to call little iota for the identity element in Sn. I'll leave you to think about why that's true. If you've got disjoint cycles, then no power of one can be a power of the other. I mean, it's basically because if a power of one was equal to a power of the other, then it would have to leave every element fixed if they're disjoint. I'll let you think about that, and I hope that at least one of you will ask about it in next week's tutorial. Okay? But I don't want to prove every last little thing today. But the point is then that pairwise these satisfy the hypotheses of the theorem. So what we can deduce then is that the order of sigma, and this is a really important result, well, it's important in that it saves you a lot of work. I think one or two of you in the tutorials yesterday had computed some of these orders just by doing it longhand by computing powers, which is fine, but this is a lot quicker. So what we get is the lowest common multiple of the orders of these cycles. So this is the extension to more than 2. In the theorem, in the lemma we've just proved, we just had a product of 2 things. Now we've got a product of u things. Sorry, I shouldn't use the word thing, it's a bit sloppy. But I'm using the extension now. So we take the lowest common multiple of all these numbers. And notice, by the way, this is just the length of TOR1, etc. Because remember, the order of a K cycle is K. So the order of a cycle is easy to compute, it's just its length. So this is a really important result. Well, it's a really useful result. Because it tells us how to work out the order of any permutation, as long as we've written it in terms of product of K's, of disjoint cycle. So that's an application of our lemma. So let's do an example of it. So let me just write this up again. So sigma was a product of disjoint cycles, and the order of sigma was the lowest common multiple of, let me just write it out the way I wrote it. So let's do an example. So let's take, say, sigma in, say, S. Well, let's use the numbers I mentioned a few minutes ago. Suppose I take sigma in the symmetric group on 10 objects. Say sigma is the permutation, which is a product of 2 cycles, a 6 cycle and a 4 cycle. Okay? So this has 2 orbits. The orbit structure of this, 1, 2, 3, 4, 5 and 6 live together in one cell, and 7, 8, 9 and 10 live together in the other cell. Remember, we call these orbits when we've got a partition arising from a permutation. So it's a product of a 6 cycle and a 4 cycle. Then straight away we can order of this without having to compute all the powers of sigma. So it's the lowest common multiple of the order of 1, 2, 3, 4, 5, 6, lots of brackets and pointy brackets, and the order of 7, 8, 9, 10. Oops, I've run out of space. Sorry. So there's round bracket, pointed bracket, vertical line, round bracket on the right hand side there. So this 1, 2, 3, 4, 5, 6 is a 6 cycle. So its order is 6. The other thing is a 4 cycle. So the only computation we have to do is to compute the lowest common multiple of 6 and 4. And we've got the order of sigma then. And the lowest common multiple of 6 and 4 is 12. So the order of sigma is 12. And if you wanted to sort of convince yourself more that this was true, you could just take sigma and compute powers of sigma, say positive powers, and the first positive power of sigma, that's the identity you would find, is 12. But that would be a bit of a pain having to do that. So this is a much easier way of doing it. Of course, if these numbers were much bigger, or if there were lots of them, you might want to use some software to compute the lowest common multiple. But we've reduced the problem of finding the order of sigma to computing a lowest common multiple. So once again, we're solving a group theory problem, which is computing the order of an element, to a number theory problem. So we've seen that once or twice. Okay, so a problem in group theory is one bit of maths, and we've translated it into a problem in another bit of maths, another area of maths, namely number theory. So there are some more examples of such computations on the worksheet, and there's a related thing on your coursework you'll see when you get it. Okay? So if you're a bit rusty on lowest common multiples, you might want to just revise that. But I guess you met lowest common multiples when you were at secondary school, did you, or at some point? You've all met lowest common multiples before? Did you do much with them last year? Probably, perhaps not. No. Well, you're all happy that the lowest common multiple of 6 and 4 is 12? You're not? Okay, well, so if we've got 6 and 4, we want the lowest common multiple of 6 and 4, let's call it 12, is what we do is we look at all multiples of 6, and we look at all multiples of 4. So we could look at the set of all multiples of 6, the set of all multiples of 4. What we want is a multiple which is both of 6 and of 4. So in fact what we do is we look at the intersection of these two things, because that'll be all the multiples of 6 and of 4, and then we want the smallest element here. So this set here is, well, we're all sorry, I should have said all positive multiples. So this set contains 6, 12, 18 and so on, and this set contains 4, 8, 12, 16 and so on. So the intersection of these contains in fact 12, 24, 36 and so on. Oops. Okay, so these are all the multiples of 6 and of 4, and the smallest one is 12. Is that okay? That's what the lowest common multiple is. It's the lowest multiple of, it's the lowest number, smallest number, which is a multiple of both of them. So okay, Yolanda, is that? So as I say, I think one or two other people might want to just do a little bit of brushing up on lowest common multiple, because we use some properties of it. For instance, and we can illustrate this here actually, any other multiple of 6 and 4 is a multiple of the lowest common multiple. So for instance, 36 is a multiple of 6 and of 4, and that is a multiple of the smallest one. We use that in our proof. Everything on this list is a multiple of 12. 12 is the smallest one. Is that okay? Yolanda, is that? So, as I say, one or two others might want to do a bit of revision on lowest common multiple. So it's a kind of basic number theoretic property, concept, and it's related to the greatest common divisor, and some of you will know the relationship between them. Does anybody know the relationship between the... So we've got M and N, say. We've got the greatest common divisor of M and N, and we've got the lowest common multiple of M and N. So this is the largest number, which is to of both M and N, and this is the smallest number, which is a multiple of both M and N, and there is a relationship between those two numbers. So for 6 and 12, for instance, if we took M equals 6 and N, 6 and 4, the greatest common divisor of 6 and 4 is 2, and the lowest common multiple of 6 and 4 is 12. What happens if I multiply 2 and 12? And what's 24? Aisha? Exactly. And that's true in general. So if you've got one of these two numbers, you've got the other. So you might prefer to compute the greatest common divisor of 6 and 4 and then divide that into 6 times 4. I mean, that requires a proof. But it does show that once you've got one of these numbers, you've got the other. Has anybody seen that before, that relationship? So that's quite useful. One or two of you seen that before. So we had, I mean, actually, perhaps there ought to be a little bit more number theory in level 1, because we do use it. And it's number theory is one of the oldest parts of mathematics, and it's the bit of maths that deals with positive integers. So it's a very basic part of maths. Of course, there are some really, really deep problems in number theory. Some of you may have heard of what was called Fermat's last theorem, which took 300 years to prove. So there are some quite deep problems in number theory, but it is about positive integers. So it's about the fairly objects. It's not about some high dimensional calculus or something. It's about 1, 2, 3, 4, and so on. Okay, so it's worthwhile you're doing a few more examples like this. We could apply this to where we had more than 2 factors in the decomposition. You just take the lowest common multiple of all the numbers. So there's some practice on that on the worksheets. The worksheet for the coming few days, which has appeared on Blackboard this morning. And so perhaps expect questions about that next week. And there is something on the coursework related to this. Okay, so you might have to do a bit of brushing up on lowest common multiple anyway. So we're reducing group theory to number theory. Okay, let me just say what we're going to do for the rest of the class, although I'm probably not going to get quite as far as I'd hoped because of the fire practice. And then I'll just say this, then we'll have a little break. So I want to talk about Cayley's theorem. So this is a little advert before the break, if you like. So this basically says that every group, any group at all, not every group is a symmetric group, but every group is isomorphic to a subgroup of a symmetric group. So we talked a little bit about subgroups of, for instance, the symmetric group S3 in one of the tutorials yesterday. So we've already met subgroups of symmetric groups. And what this says is any group you like, take your favourite group, it might not be a symmetric group. For instance, if it's finite, if it doesn't have order equal to n factorial for some n, it's not equal to a symmetric group, but it's isomorphic to a subgroup of a symmetric group. In other words, you can think of any group as a group of permutations. So although when we started this topic of permutation groups last week, it looked like it was a special part of group theory, in fact it's very general in the sense that every group can be thought of as a group of permutations. So this is Cayley's theorem, named after Arthur Cayley, English mathematician of the mid-19th century, who did a lot of early work on group theory and abstract algebra. So we're going to look at that. I'm not sure if I'm going to be able to have time to do the proof today, but perhaps we'll do an example of that. And then I also want to talk about a particular subgroup of the symmetric group called the alternating group. So this is another group to add to our list of examples of groups. We haven't actually had any new groups for quite a while. And the alternating group is one of the few new groups we're going to meet now in the rest of the semester. So the alternating group, well, it's actually a whole sequence of them. Each Sn has a special subgroup called the alternating group. Usually this is for n bigger than or equal to 2. Well, it is for n bigger than or equal to 2. And this is a subgroup. Remember, this is just an advert. I'm not actually doing the topic now because I'm not telling you anything. So here's Sn. Here's a very bad division of this oblong into 2 equal parts. But this is An. And it's a subgroup with exactly half the elements of the symmetric group. I hope you can all draw a better oblong divided into 2 equal oblongs than I can. So the order of An is a half of n factorial, because remember the order of Sn is n factorial. So this is a very special subgroup of the symmetric group. And basically, the way you construct AN is you think about 2 cycles. Okay, cycles of length 2, and another word for those is transposition. And it turns out, as we'll see, you can write any permutation as a product of 2 cycles. That's another way of breaking up a permutation. All that says is, if you've got some reordering of 1, 2, 3, 4, 5, 6, 7, say, you can get that reordering just by swapping 2 of them at a time. And you might have to do quite a lot of swaps, but you can get that reordering just by swapping 2 at a time, and there are various puzzles and card tricks based on this, actually. And it turns out, though, although there's lots of different ways of ordering your swaps, if a permutation can be written as an even number of these swaps 2 at a time, it can never be written as a product of an odd number and vice versa. So you can divide permutations into ones which are a product of an even number of transpositions and those that are a product of an odd number of transpositions. It's either or, and there are none that can be done in both ways. And AN are all the even ones. So these are all the permutations that can be written as a product of an even number of 2 cycles. So we're going to discuss this in more detail, and there's various things to prove such that this definition of even does make sense, and then this is a subgroup. So for instance, if I took the 3 cycle 1, 2, 3, it's easy to check that that's equal to 1, 3 times 1, 2. I can do that 3 cycle as a product of those 2 transpositions. Remember, 1, 2 comes first, then 1, 3. So here are 2 transpositions, so we say that 1, 2, 3 is an even permutation because it can be written as a product of 2 transpositions. There's a slightly pesky fact that cycles of odd length are even. It's just one of those pesky facts in the universe. And that cycles of even length are odd, but you'll remember that. Anyway, we'll talk about that in the second half, hopefully. So let's have a 5-minute break, and we'll resume then.